This movie introduces a study of a multiplicative Schwartz type block multicolor Gauss-Seidel smoother for a multigrid method. This smoother is new and useful smoother compared with existing. In a field of computer simulations, a fast solver for solving systems of linear equations is required. It is because SLEs are derived from almost physical simulations and consume most of the simulation time. The multigrid method is an effective method for solving such SLEs. The multigrid method is one of the iterative methods. The iterative method is suitable for solving SLEs with a sparse coefficient matrix. Significantly, the multigrid method shows a higher convergence rate compared with any other iterative methods. Then, we focus on developing a fast multigrid method. The high convergence rate of the multigrid method strongly depends on aggregation, restriction prolongation operators, and smoother. Significantly, the smoother decide not only convergence rate but also computational cost per one iteration. The smoother is executed twice in each iteration. And the choice of the smoother decides the difficulty of parallelization. Basically, the smoother, which is challenging to parallelize it, shows a better convergence rate. In this study, we focus on the smoother. In this page, we introduce existing smoothers. The sequential Gauss-Seidel smoother is a basic one, and it shows good convergence. However, this smoother is difficult to parallelize. The convergence rate of the sequential Gauss-Seidel smoother is often a criterion. The multicolored Gauss-Seidel smoother is one of the parallelized Gauss-Seidel smoother. The convergence rate of the multicolored smoother achieves a similar to sequential Gauss-Seidel smoother. However, the data locality of this smoother is lower than the sequential Gauss-Seidel smoother. A block multicolor Gauss-Seidel smoother solves the problem of multicolor Gauss-Seidel smoother. The block multicolor Gauss-Seidel smoother is a multicolor Gauss-Seidel smoother with blocking technique. This technique increases data locality. The block multicolor Gauss-Seidel smoother looks the best smoother for the multigrid method. However, the proposed smoother showed a higher convergence rate and data locality than the block multicolor Gauss-Seidel smoother. The superiority of a multiplicative Schwartz type block multicolor Gauss-Seidel smoother is high convergence rate and data locality. If we apply beta times existing smoothers, it requires beta times computational cost per one iteration. To reduce the total computational time, the convergence rate of the multigrid method must be increased twice. In the MS-BMC-GS, we apply alpha time GS steps to each block repeatedly. Thanks to the cache, the computational time for one smoothing step is not increased by a factor of alpha. The improvement of the convergence rate caused by the increasing number of GS steps in the block may reduce the total computational time. In this slide, we show the difference between BMC-GS and MS-BMC-GS. This picture shows the example of MC-GS. The numbers show the order of updating nodes. By applying the multicoloring technique, the data dependency among each node are removed. Then, we can parallelize Gauss-Seidel smoother. This picture shows the example of BMC-GS. By applying the blocking technique, the data locality is increased. The convergence rate and data locality of BMC-GS is similar to the sequential Gauss-Seidel smoother. This is the example of MS-BMC-GS. In the MS-BMC-GS, we apply the GS steps to each block continuously. Thanks to the cache, the increased computational time is smaller than the amount of increased computations. These graphs show the performance of a geometric multigrid method with MS-BMC-GS. The left graph shows the performance with OpenMP intranode parallelization, and the right graph shows with MPI parallelization. On each parallelization, MS-BMC-GS shows the best performance compared with existing smoothers. With the intranode parallelization, MS-BMC-GS shows 15-time performance improvement based on sequential Gauss-Seidel smoother on 16 cores. With the internode parallelization, MS-BMC-GS shows 15-time performance improvement on 216 cores. These graphs show the performance of an algebraic multigrid preconditioner with MS-BMC-GS. The based iterative method is a conjugate gradient method. The difference among graphs is targeted problems. In each graph, the bars show the computational times, and lines show numbers of iterations. On any problem, the MS-BMC-GS shows better performance than BMC-GS. In the best case, MS-BMC-GS shows a 14% performance improvement than BMC-GS with a parabolic FEM problem. This is a conclusion. Thank you for watching this movie.